Welcome to In 5 Minutes. In the previous video clips, we have defined FM and PM signals mathematically. We had also discussed two ways to generate FM and PM signals. For example, if I want to generate FM signal, then I can change the frequency of the carrier signal directly in proportion to the modulating signal amplitude, or I can also change the phase of the signal in proportion to the integration of the modulating signal. Both these approaches will ultimately result in frequency modulation. And because of two different ways of generating FM and PM, we have two types of FM and PM generation methods. The first one is called direct methods and the second one is called indirect methods. What we are going to discuss in this video clip is the very simple block diagram of indirect way of FM and PM generation. Let's say that we take a modulating signal M of t, and let's say in this first block diagram my aim is to ultimately generate FM signal. We all know that to generate FM signal we will have to vary frequency in proportion to M of t amplitude, but instead of varying frequency, because that will become the direct method of FM generation, so instead of varying frequency of carrier we will vary the phase of the carrier signal. To vary the phase of any sinusoidal signal, we will need something called as phase modulator. So the block that I'm taking is that of phase modulator, and to the phase modulator, we will give the carrier signal cos omega ct. So this carrier signal, which has the initial phase of 0, when it is given to the phase modulator, it will change phase of the carrier signal. But it will change phase of the carrier signal in proportion to what? In proportion to the input signal that goes to the phase modulator. Now, to generate FM, if you are changing the phase, then phase must be changed in proportion to the integration of modulating signal. So somehow I have to generate integration of the modulating signal and give it to the phase modulator. This will ultimately give me FM signal at the output. To generate integration of any signal, the very obvious block that we are going to use is the integrator. So the very first block that we have in this whole setup is of integrator. So take an integrator, integrate the modulating signal, give it to a phase modulator, and that will give you FM. So this is indirect way of FM generation. Similarly, let us now consider a very much similar setup, but this time my aim will be to generate phase modulated signal. So we have a modulating signal M of t, and because I want to generate phase modulation, I should be changing phase of the carrier signal. But if I do that, it will become a direct method of PM generation again. In the indirect method of PM generation, something that we are discussing right now, we should be changing frequency of the carrier signal. So the block that we have in the entire setup is nothing but frequency modulator this time. So what will this frequency modulator do? It will change the frequency of the carrier signal from its original frequency of Fc. Now how will it change the frequency? It will change the frequency in proportion to the input signal which is given to the block itself. Now we have already discussed that to generate phase modulation, the frequency should change in proportion to the derivative of modulating signal. So what I want to generate first is d by dt of M of t and then give it to a frequency modulator, and my output will be frequency varying in proportion to derivative of M of t and hence phase varying in proportion to M of t amplitude directly. So that will become my PM signal. And to get derivative of any signal, we will use a very obvious block of differentiator. So what you need as the first block in this second setup is nothing but a differentiator and give it to a frequency modulator. So what we have just now discussed are nothing but the indirect methods of FM and PM generation. And along with this indirect methods, let me also quickly once again write down the final expressions of both FM and PM signals, because we will keep using these expressions in the further analysis of the signals. So we have already derived FM and PM expressions. I'll start with the FM expression. FM signal we had written as Vc cos omega ct plus, if you remember, the constant in that case was 2 pi kf, and the phase is proportional to integration of the modulating signal, and the frequency will automatically be proportional to modulating signal itself in that case. And PM signal was equal to Vc cos omega ct plus the phase is directly proportional to modulating signal. So in place of phase expression, we simply write kpm of t. So these are the standard expressions of FM and PM signals. Very important, because whatever analysis we do with FM and PM signals will be first starting with this expression. For example, we'll be soon deriving the frequency spectrum of FM signal so that we can find out its bandwidth. And to derive the frequency spectrum of FM signal, we will start with this expression.